Yes, this felt like a very long week, and I was even gone a day. So today, well, let's really start. Last time, I'd asked you guys to work on sections 1 and 2 kind of on your own. Today, I'm going to carve out a big chunk of time here to start to just kind of handle questions. So they can be specific homework questions. They can be general conceptual questions. They could be about something you read in the notes or read in the lessons or saw in the video and you just weren't quite sure on, that you just need some clarification on. Or it can be like, I was working on this problem and I don't have any clue what to do with this. But this is going to be the plan for a good chunk here to start. Is just, you've done some work on your own. We're going to kind of come back together and clarify some of these points that maybe didn't sink in all the way or still a little bit hazy or whatever. Okay with that plan? So it's your guys' time to kind of tell me what you want to work on or what you want to go over and any of that kind of stuff. So if you're not sure about something, or if you've started and got stuck someplace, or you're just like, I looked at this and I already know it's going to be a problem even if I haven't really gotten there yet, any of it's fine. Okay? Okay, Rochelle, we'll start with 31, you said? Okay. Certainly. Actually, I'm just going to do them all on the side. I have the printout here. That'll be easier. So it says, find the exact value without using a calculator. So sine of pi over 6. So when I ask you to find the exact value for a trig function without your calculator, it's going to entail either using the 30, 60, 90 or 45, 45, 90 triangle. So from geometry, we remember the 30, 60, 90 triangle had side lengths with ratios x, x square root of 3, and 2x. And the 45, 45, 90 triangle has side lengths with ratios x, x, and x root 2. So the question for us is, okay, pi over 6 either needs to be 30, 60, or 45 for me to be able to do this. Which one of those is it? So we'll just start by converting that radian measure into degrees by multiplying by 180 over pi. So that's going to come out to be 30 degrees when I do that. So really what I want is sine of 30. Okay, so 30 degrees is here. Sine is opposite over hypotenuse. So I have x over 2x, which reduces down to 1/2. Does that feel okay? So all of these, 31 through 34, you're going to be using either that 30, 60, 90 or 45, 45, 90 triangle. And these are triangles that are going to come up again in the next chapter and possibly the chapter after that even. So these are good things to make sure that you're familiar with. Like find a place in your notebook, write them in, put a big box around them so you can find them later. Because they are things that you'll want to be able to refer back to if you don't have them already memorized. Because they will be things you'll use again in this chapter and the next chapter, and I think maybe the chapter after that. I can't remember for sure. Okay. But you're happy with that, Rochelle, with what we did there? Okay. Leo, did I see your hand coming up earlier?
Yeah, I was just going to ask if to find radians that you go from, that you solve times it by 180 and find degrees times by pi over 180.
Right. So if you want to go degrees to radians, here you're going to be multiplying by pi over 180. And if you're going from radians to degrees, you're going to be going the other way. You multiply by 180 over pi. And I think the easiest way to remember this is it's like a unit conversion kind of thing. Like if I have 60 degrees, when I multiply by the conversion factor, the degrees need to be in the denominator, and the radian part has to be in the numerator, so that when I multiply, like the degrees cancel, and I'm left with, you know, something in radians. Does that make sense in terms of remembering which one to go with which one? If you think about it like a unit conversion, it becomes really obvious kind of which way to put the fraction. That's the way I like to remember it. So that's just like a side. I'll just put like a little box around it so it's not if you go back and look at this stuff, you're not confused about what problem that went with. So it's just an example or whatever. Okay. Joe, was your hand up earlier?
Yeah. Can you do number 19, the short column one?
Yeah, sure thing. So 19 says two concentric circles are cut by the same angle. So when we say concentric, what we mean is two circles that have the same center. So you have like one circle is like inside of the other one. So it looked kind of like that. Oops. And we have them cut by the same angle. So there's my angle. So far, so good with the picture I've drawn. Okay, let's label some parts to it. So I'm going to call R1 the radius for the little circle. S1 is going to be that arc length on the little circle. R2 is going to be the radius on the big circle. S2 is going to be the arc length on that big circle. And theta is the same because the same angle is forming both arcs, right? Okay. It says the radius of the smaller circle is 4.3 inches and the cut arc measures 5.2. So right there, I know I have enough information to solve for theta. Now, remember there's two versions for this arc length formula. There's one when the theta is in radians and another when it's in degrees. It doesn't really matter which one you use. Just keep in mind you'll be getting an answer that's in radians if you're using the formula I'm using versus degrees if you use the other version. I'm going to use the radian one because it's the final answer here. We're not looking for the angle, so it doesn't really matter what unit you use because it doesn't ask us for a specific unit. So I'll just divide both sides by 40 or 4.3. So 5.2 divided by 4.3 is going to be 1.209. It says the radius of the larger circle is 5.2. What is the length of the cut arc? So here I have the radius is 5.2, we're told in the problem. And that cut arc is what we're looking for. That's the S2. But we know from the previous one, the theta is 1.209 radians. So I just need to multiply those two together. And that'll be my answer. So 6.29, I think it said round to the 100th, yeah. And the measurements here were in inches, so we're in inches again. So just to kind of reiterate, what we did is we used this smaller situation to solve for the theta, and we used that theta to solve for the bigger situation, the arc length in the bigger situation. Joe?
So the 1.209, that's what you get when you divide the 5.2 over the 4.3.
Yes.
And then, so you're using the 5.2 because the 5.2 is representing.
So the 5.2 was two things in this. Their S1 was 5.2.
Yeah.
And R2 also was 5.2. So the question had two different measurements that were both length 5.2.
So like if R2, for example, was like 6.3, then you would have done 6.3 times 1.2
Yes.
to get your answer?
Yes.
And does it tell us the R2 in the problem?
Yes.
Okay.
Yeah, so again, to read the problem all the way from the beginning, it says two concentric circles are cut by the same angle. The radius of the smaller circle is 4.3, and the cut arc measures 5.2. If the radius of the larger circle is 5.2, what is the length of the cut arc?
Oh, okay.
For the larger circle? Round your answer to 2 decimal places.
Okay, sounds good. Thank you.
Yeah, no problem. Maybe I should have read through the whole problem before I started picking it apart. You know, like trying to be clear, right? I end up reading through the whole problem anyway. I should have just started with that. You know? Who's next? Again, we can do as much or as little as you guys would like. We can talk about specific homework problems. We can talk about conceptual stuff. I'm happy to do any. Leo?
You do on like 29 or 30.
29 or 30? Sure. Do you have a preference there? Let's do 30 so you guys can do 29 and check your work. How's that sound? That's maybe the better way of going on about it. So it says that the directions here are important. It says assume that theta is an acute angle in a right triangle. So I'll start by drawing that. Doesn't really matter where I put theta, so I'm just going to put it down in that corner. Either angle, though, is fine. It just has to be one of the acute ones, not the right angle, obviously. That satisfies the given conditions, and then find the value for the 5 other trigonometric functions. Okay? So the secant theta equals 11 over 5. Remember that secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. So what I'm going to use that is if I look at my triangle, relative to my angle theta, this side is the adjacent, this side is the opposite, and this side is the hypotenuse. So I know that this side is 5, and this side is 11. Leo, are you happy with what I've done so far? Yeah. Okay. I can use the Pythagorean Theorem now to find the opposite side, since this is a right triangle. Remember the Pythagorean Theorem, the hypotenuse has to be the C. Doesn't matter which leg you call A or which leg you call B. So I'll have 5 squared plus B squared equals 11 squared. So 25 plus B squared equals 121. Subtract 25 from both sides. And then we'll square root both sides. That's 4 square root 6, or you could make it a decimal if you want. I'm going to use the radical. Is that okay so far? I think it asked for, I guess it didn't tell you how it wanted the answer. I would say on a problem like this, I would expect exact answers. So fractions with radicals in it would be my expectation, but so far so good. Yes or no? Doing okay?
Yeah.
That sounded hesitant.
I just forgot how to get the 4 root 6 from the 96.
Oh, okay. So I'm going to just try to break 96 up into the product of like a perfect square and something else. So 96 is 16 times 6. And the square root of 16 is the 4. You might have to draw the prime factorization tree. That could help. But I recognize 96 is 16 times 6. So I just took the shortcut with the perfect square already staring at me. Is that cool?
Yeah.
Okay. Okay. So now that I've found all the side lengths, I can find the values for sine theta, cosine theta, tangent theta. I already have secant theta, so I don't need to do that one, and cotangent theta. So relative to my angle theta, sine is opposite, so that's the 4 root 6, over hypotenuse, that's the 11. Cosine is adjacent, that's the 5, over hypotenuse, that's the 11. And tangent is opposite, that's the 4 root 6, over adjacent, that's the 5. Cosecant is the reciprocal of sine, so that's 11 over 4 root 6, or you could think about it as hypotenuse over opposite. But I don't want to leave my final answer like that because we have that radical in the denominator. So I'll just multiply the top and bottom by root 6. So the numerator I'll have 11 root 6, and the denominator I'll have 4 times root 6 squared. Now root 6 squared, the root and the squared are going to cancel out. So in the denominator, really, I have just 4 times 6. Or 24. And then the last one, cotangent, is the reciprocal of tangent, or you could think about it as adjacent over opposite. Again, I'm going to rationalize the denominator doing the same thing I did before. So just multiply the top and bottom by root 6. I guess I'll show it. So the top I have 5 root 6. And the bottom I have 4 times square root 6 squared. The squared and square root cancel. Oops. So I have 5 root 6 over 4 times 6, which is 24. So those are my 5. The summary here, Leo, is that basically after you've built your triangle, it's the same kind of problem as 25 through 28, right?
Yeah.
That's the big takeaway. It's just like, okay, can I take that, sine theta or cosine theta, in this case secant theta equals, and turn that into a triangle. So you basically just assign you pick a theta and then you assign the opposite and adjacent or hypotenuse, whatever you're given, to the right spots, and then use the Pythagorean theorem to find the third one. And then it's just like the previous problems. Again, if I'm going too fast through something, or if you're not sure on something I did, or you need some more clarification, or you're like, I don't even know what that thing is, like, no embarrassment, just stop me and ask. Like, this is what this time is built for, is to kind of clarify some stuffs, ask you to do some stuffs on your own. So if you're confused on something, like, that's okay. There's no bad questions. Joe?
On your I think it's cosine theta for the 11 over 4 times the square root of 6.
That's cosecant. CSC is
Oh,
for
CSC,
cosecant.
okay. Yeah, so when you're solving that, and like I understand how you got rid of it, you canceled everything out. Is that an L before the 4?
That's a 2, is
Oh,
what
it's
that's
2?
supposed to be, 24.
Oh, 24? Okay, yeah. My fault. I didn't know what it was.
That's okay. My penmanship is,
You're good.
suboptimal at times. So I don't mind answering those kinds of questions. Like I can't tell what that symbol is. Makes it a lot easier to understand if you can read it, right?
So you're basically just following the steps of the SOHCAHTOA.
Yeah.
And you're plugging in your variables.
Yeah.
That's it.
Yeah, you're basically using SOHCAHTOA to build your triangle, and once your triangle's built, you're using SOHCAHTOA to fill in the other trig functions.
Okay.
Ariana. Sure. Do you have a preference there? Okay. Let's do 36, I guess. So that says cotangent of 11.9 degrees. So I notice here that this is in degrees, or actually, excuse me, let me read the direction. Evaluate using a calculator. Round your answer to the nearest 1,000. So first thing I'm going to notice when I fire my calculator up is the angle in this question is in degrees. So I'm going to check my calculator straight away to make sure that it's in the proper mode, because if I'm in the wrong mode, I won't get the right answer when I do this. So I'm going to press the mode button here next to the blue second button. And I'm just going to make sure that I am in degree mode, since this problem, the angle is in degrees. If you're not in degree mode, you just use your arrow key to move over to where it says degree and press enter till it's highlighted. And then you're in degree mode. And then you can exit back out. So I'm in degree mode. Now, in my calculator, I have sine, cosine, and tangent right here for me. The problem is that this this question has cotangent. So the way I'm going to take care of this is I know that cotangent is the same as the reciprocal of tangent. So I can just do tangent, or I said 1 over tangent of 11.9. So I can do that on my calculator, just with the division symbol. I could do like 1 over tangent of 11.9. So that answer should be 474.5. You okay so far, Ariana? Okay. Worth noting that you could have also used the reciprocal button. So you could do this as tangent of 11.9. And then this button, the x to the negative 1 is the reciprocal button. So you could do it that way. You get the same answer. What's not the same, though, is if you use tangent inverse. So you notice in blue above tangent is tangent to the negative 1. That's not the same thing as tangent of 11.9 inversed. Tan inverse of 11.9 gives us a decidedly different number. Okay, so that's not what you want to do. But we were done here when we got the 474.5. I just wanted to clarify some stuff on the calculator. So what's the difference between like cosine and cosine inverse, right? That's probably a reasonable question since we just kind of talked about that. So this will just be a little aside. So cosine theta, what it does is it takes an angle and turns it into like a ratio of side lengths, specifically like adjacent over hypotenuse. Cosine inverse is going to take a ratio of side lengths, like adjacent over hypotenuse, and turn it into an angle. So on my calculator, what this is saying is that 11.9 over 1, so if the opposite side is 11.9 and the adjacent side is 1, the angle there would have been 85.196 degrees or whatever. Is that okay with the difference between what the two things are doing? Okay. So like if we have a right triangle and we're trying to find, you're given the angle and a side, and you're trying to find another side, here I would use like tangent. But if you're given, say, like a triangle and you're trying to find the angle, here you'd say like tangent theta is opposite over adjacent. So to get rid of the tangent on both sides, you do like tan inverse to both sides. So that's like how we get the angle back, if that's what we're looking for in the triangle. Does that help getting a little bit more specific if the difference between that? So again, cotangent, reciprocal, tangent inverse, not the reciprocal. It's a function. It's a different function that gives you an angle back instead of a ratio of side lengths.
I go to the bathroom.
Of course. And again, I realized somebody pointed out to me earlier today that like these ideas would have been things that you would have done in the end of your geometry semester, which was when we were all online, which might not have been done that well. So worth taking a few minutes and kind of rehashing like what exactly we mean by sine, cosine, and tangent. Like what are these things doing? You know, what is the inverse doing? Like how do I get an angle back? Or how do I find a side length? Like these are all things that ideally is prior knowledge from geometry, but might not be that well done if it came from that time. Typically, this is something that's done at like the second half of second semester in your geometry course, which I think would have been all online last year, or 2 years ago, excuse me. So, again, if we're feeling foggy on that kind of stuff, please stop me and we can go back and reteach, since it's probably everybody's in that same kind of fog. So don't be shy about that kind of thing. If you feel like there's a hole somewhere and I don't get what's going on, really, it's probably we're missing some background, and you got to help me out there in terms of figuring out what we're missing. I can probably kind of figure it out, but if I don't know something's missing, it's hard to realize until it's, you know, we start grading tests and stuff and go, oh my God, what is going on here? Okay, so again, if it feels like something is missing, please say something and we can try to sort some of that out. Yeah, 44? Certainly. So just, I don't think I wanted you guys to do through 40 or through section 2.3. 44 is in section 2.3. We can talk about it, but it's not part of your homework set for this week. But I'm happy to take a minute and talk about it. So I just want to make that clear that I think through 42 is your problem set for this week. I think that in my agenda originally, I thought we were going to get through section 2.3. I don't think that's going to be realistic. So I certainly wouldn't have asked you to do 3 sections on your own. I think that's a bit much for this course. But it's fine. We'll talk about it. But just so everyone's, if you listen to the 2 videos like I'd asked you to, and you're like, what in God's name is he talking about? I don't remember any of this from sections 2.2 and 2.1. That's because it all came from 2.3. Okay, so just, Riley? Okay. Of course. All right, but we'll talk about 44. It's not a big deal. It says, find values of 2 different angles coterminal with the given angle One of your answers must be positive and the other must be negative. So before we can do this, we have to talk about a little bit of some definitions. So in section 2.3, we define a new way to draw an angle. This is called the standard form for an angle. What we do is we embed that angle on the xy axis, where the vertex of the angle is at the origin, and one arm of the angle is on the positive x-axis. And then if we wanted to, say, draw a 120-degree angle, we rotate the other arm of the angle 120 degrees, where it's kind of the pivot point is at that origin. So going here to here is going to be 90 degrees, every quadrant is 90 degrees. And then it would go 30 degrees more. So the other arm of our angle would go here. We call this arm on the positive x-axis the initial side. And this arm we call the terminal side. So if we want something coterminal, that's another angle whose terminal side is in the same location. So if I drew, say, this green angle, I start there, and I go one full time around, that's 360 degrees, and then do 120 more, that would be 480, would end up at the exact same location. We'd say that those are coterminal, because the terminal sides lie at the exact same location. So what it basically comes down to is that all I need to do is go another rotation, either forwards or backwards, and I'll end up at kind of the same spot, right? So in the case of forward, we'd be adding. We say when we rotate counterclockwise, that's a positive angle. And when we rotate clockwise, that's a negative angle. So all we're really going to be doing is adding or subtracting 360, and that'll generate a new coterminal angle. Now 44, the angle that we're given is in radians. So rather than adding or subtracting 360, we'd add or subtract 2 pi. And the reason is that 360 times pi over 180 is 2 pi. So far, so good? So to get my one of these coterminal angles, the positive one, I'm going to add 2 pi. Since the angle I had to start with was positive, and I'm going to be adding a positive to it, I know I'm going to get a positive angle back, right? To add these two fractions, I need a common denominator. Should be pretty clear that common denominator is 7. So now I have 2 pi over 7 plus 14 pi over 7, which gives me 16 pi over 7. So there's one coterminal angle. If I want a negative one, I think the answer or the question asks for a positive one and a negative one. Well, I better do some subtracting. So I'm going to subtract 2 pi this time. And again, make my common denominator. Negative. 2 pi minus 14 pi is negative 12 pi. So there's a negative angle. So that would do it for us. Just hypothetically speaking, if I subtracted 2 pi and I didn't get a negative angle, what would I do?
Didn't get a negative angle?
Yeah. I would just subtract 2 pi again. And just keep doing that until I got a negative. I just keep doing it over and over and over again. It's just basically, you're doing more than one loop around the circle, but you can do as many loops as you want, as long as you end up at the same spot. It's still coterminal. Whether you did one loop before you got there, or you did 1,000 loops before you got there, it's coterminal. of these first three sections, this idea of like being able to draw a standard form angle and this idea of coterminal is probably the most important idea going forward. So like being able to draw these angles that are bigger than, bigger than 180 or bigger than 360 or are negative or whatever is like a really important skill kind of going forward. So just kind of keep that in mind when we get there. We'll redo all of this that we just talked about when we talk about section 2.3, but we asked about it. So I'll, feels okay? Not terrible. No, again, like for the most part, here's the thing with this course, really most of the stuff we do is not terrible. The problem is that what you did before matters in the next chapter, and then matters in the next chapter, and matters in the next chapter. So if you don't hang on to it and do a good job of retaining it, things get very overwhelming in like 2 or 3 chapters. So that's one of the big challenges for this course is that you really have to kind of stay on top of everything, if you know what I mean. So you really kind of get hammered if you fall behind, because then nothing starts fitting together the way it needs to, and like really lots of gaps start forming, and it's tough to kind of get caught back up, especially first semester. First semester in particular is very, very tough if you're not kind of keeping up with things. So just as a, Ariana? Mm-hmm.
I can do that by dividing the thing by 2 pi.
So really what you want to do to go from radians to degrees is just multiply by 180 over pi. That's going to just be the fastest way to do it. Like what you described, I think is fine because the 360 and the 2 pi reduce to give you 180 over pi. So just, I think that was fine. I think I understood the order you're trying to do that in, but like, I think it'll work. It's just not very efficient. You know what I mean? Do you guys want to talk about some more stuff? Joe?
Okay, I have a question, a general question about 1 through like 12
Sure.
on the homework. Whatever that was, like vector conversions.
Yeah.
Okay, so when it asks to put it into pi, so like that's the
Oh,
fraction
in
form.
terms of pi.
In terms of pi,
Yes.
yeah, in the fraction form.
Yeah.
So I understand how to do that, but if we have a decimal point, like for example number 2,
You're not going to do that.
So we can't. We just keep it in like the answer. I think is 0.34.
Sure.
We just keep it at 0.34 radians.
Yes.
Okay.
Yes.
Okay.
So like on 1 through 6, the directions say leave your answers in terms of pi when applicable.
Yeah.
Basically, that's saying that if you have a decimal, you're not going to be able to turn it into a fraction easily. We're going to ignore that.
Okay.
And then I would have to look at number 6. 289 might be a prime number.
Okay.
That might be one also that if like there's no reducing to do, it might just be,
Yeah, it's just 289 over 180. It doesn't change.
Yeah, so if that's one again where if you made it into a decimal, I wouldn't complain about that.
Okay.
You could leave it as 289 over 180. Like I'm not going to complain about that either.
Yeah.
But that would be one that it would be not unfair to make it a decimal since there's no reducing.
Okay.
Especially if the directions are as ambiguous as that. If I asked for everything in terms of pi, then put in pi. Just leave it as 289 over 180 or 289 pi over 180. It's like, okay, that's all I can do. Would be fine. And if I asked for a decimal and you gave me it in terms of pi, I probably wouldn't mark it wrong. But if you gave me the decimal when I asked for in terms of pi, I would make a deduction for that.
Okay.
And the reason there is that the exact answer that's the thing in terms of pi where there's no rounding involved, is always preferable to a rounded answer where you make a decimal and you have to do any rounding. So if you give me the more precise answer when I want the approximation, I'm not going to mark that wrong. But if you give me the approximation when I want the exact, I would mark that down. And that's kind of in general, right?
Yep.
And that hopefully that makes sense as to why, like, the more precise answer is okay to give when I ask for a less precise one, but to go the opposite way is a problem. Okay. Last call before we kind of move forward. Okay. If you would put your things away other than something to write with in your calculator. Let me pass these out. I'll bring the one in a second,
Degree to radians is degree times 5.
Write down it. Anyone else need to borrow a calculator as long as I'm up at it? Okay. I've seen you use it before, so I'm confident you got one. You'll want to make sure you put it in your backpack for next time. But